Okay, so that's a very great meeting. And, I like it very much. I think it's a little bit scary when I see all the challenges we have as a mathematician. I think it's very interesting. So we'll try to speak about modular approaches, and I've heard about modularity during the course, and I think it's a very okay. That's some kind of idea of modularity, but no, I have discovered that it's really something that exists in biology in a very much more complex way. So it would be very simple-minded modularity. And diffeomorphometry, and so I'm used to, Laurent is saying that I'm always showing some dummies. Supposed to be the connection with biology. So I was not planning to show you dummies. Okay. Maybe I will show. Okay, so it's not opening. Okay. Okay, so. Yeah. Okay, so it's just to show you a bunny, how you can transform, how you can morph the sphere into a bunny. So I think this is the kind of thing we can do with LDM stuff. But if you see, we are very happy with that. But okay, for biologists, it makes absolutely no sense because it's just some kind of morphing. It has no structure, no. Okay, it's just a way to go from a sphere to a bunny. Okay, so we are proud of that, but I think for a biologist, it's meaningless. Okay, so what I was thinking for the last 15 years is about this how to use diffeomorphisms on shape spaces, and we used to refer to Darcy Thompson, and several of us referred to Darcy Thompson during the workshop. And it happened that I spent some time reading his book. I was talking about the book and reading the book. Okay, it was clear from his book that Darcy Thompson was saying that in fact it really was aware about everything at all the scale in biology and because I was thinking that this theory of transformation was a little bit crude in a sense, to say, because it's very crude. And reading the book, okay, I understood that, and I see that, in some of the conferences where people were talking about integration and so on, that the theory of transformation is really the idea that, at a given scale, you have so many constraints that you should have something which the transformation should be simple and smooth. So it means that the evolution, you have a lot of constraints, so you have some kind of manifold. That's why it makes sense, because we cannot really explain all the details of the physics, so at a given level we need to have a definition of the methodological. And so this theory of transformation makes sense. Okay, so I'm more interested in computational anatomy, where it's about comparing shapes, but very different kind of shapes. So it could be this images, this internal structure, this fiber bundle in white matter in the brain. And so these shapes may be so complex that in some sense that could be easy to think about just not describing really the evolution of a shape, but describing the evolution of the space transforming the shape. Because in some sense it's simple, because you have this, if you look at all these fibers, you could say that's the shape, and if you want to compare this, you could build a model of fibers, but you could say it's more simple to just to move the space. So I think this is some kind of very simplifying assumption, but it's important because shapes are usually embedded in some real space. So we can study shape as a whole, but after we have to think how shapes are embedded in space. So that's why it makes sense to. But since we are able to make connection between shape and so on, I think that morphing or matching shapes or computing distances is not in some way, it's not explaining what's happening. So I think I like to refer to this sentence by Untitled saying that, okay, asking, is it possible to mechanize human understanding of biological creatures? So can we have some something which is meaningful, shouldn't have some kind of interpretation, not just numbers. So I think we are not answering the questions. Hence, okay, some of you, but I'm not really answering the question. I'm not part of that. So I will try and talk to go in that direction and to show some attempts and some very recent work we are doing with former PhD student, which is Barbara Gris. So first I will start from say a few words about the usual framework, the simple framework, where we, in which we derive all the different algorithms for matching shape with diffeomorphometry. So Peter talked about groups this morning, so I can use group. I'm happy with that. So the basic idea is to say, okay, the first idea is to say, instead of thinking to build immediately distance between shape, it's simpler to think about distance between transformation. That's the idea. So think about distances between transformation. So transformation from a group, as we've seen several examples this morning. And so here we have, in fact, we have, and this is the very idea of Darcy Thompson, we have, what we are doing is that getting a transformation in an object, we can transform this object by transformation. So this is an action of an element in the group, G in the group. M is an object, and you can transport it in many ways. If you are in images, you deform the image. If you have points, you deform the points. And okay, if you have surfaces, and you can deform some higher differential structures. Okay, so you start from this group action, and you think that you have a space where you can go from any object in your space to any other one by just making a transformation. We call it a transitive group action. So in fact, you can say if we take a unique element, a template, you say your object space is just all the transformation. Yes. And the trick is that, and we have seen that trick several times in this conference in different ways. If you have a right invariant distance on G, I mean, if you, on the transformation, it means if the transformation, if the distance between two transformation is such that if you compose on the right by another transformation, you don't change this, so this is right invariance, then you can induce the distance on shapes, on objects, on that orbit, on that space of object by just trying to look at the shortest, the less costly transformation, transforming M in M prime. You have two objects, and you try to transform M in N prime. Look at you can have many solutions, and you try to find the cheapest one. And if you do that, you get a real distance, and you can elaborate a lot of this. So it means that you can get, if you start from distance on the group of transformation, you get distances on objects. And so you have a lot of ways. So it means you have a very cheap way to build distances on object by just building distances on group of transformation. Okay, so this is why this is a very simple thing. And so what will be the distance between two objects is that the distance between two objects, how you compute it. In fact, if you go back in the group, given your template, you can look at all the transformation which leave your template and change. I mean, when you act on N0, you do not change it. So it's where this is more or less the invariant group of your object. So you have a fiber access. So you can associate to any object a fiber in the group, and you will compute the distance between the fibers. It's a very geometry. Okay, and so with that you can define distance between on objects. But if you do that, I think okay, it's simple, it's computationally very efficient. You can transform sphere in rabbits, and rabbits in elephants, what you want. You can do this kind of thing. It's quite a lot of tricks to do that. That's okay, I think it's quite robust. But I think it's you could say, in fact, it's a little bit artificial in a sense, because you built this, you just built a distance. You are just paying attention to how you pay to transform the space, but not really. It induces a distance, a real distance on the object, but you're more thinking about the transformation of the space. So you could say that could be more, I think you could have some kind of, I think it's more or less, when you think about shape, we think about something which is much more concrete in a sense. So this approach is very non-parametric, and so people want to say, okay, I'm doing this on that shape, or something is happening somewhere, and so on. So we have, I think, this problem of non-parametric versus parametric modeling. So what we can do in this approach, we can change the metric, because to define the metric on the group, but the group will be the group of diffeomorphometric. RD. And to define the right invariant distance, what you just need is just to define a distance, a cost on the just a perturbation of the identity. Because of the right invariance, if you know the cost somewhere around the identity mapping is just you don't move. And so what is a perturbation of a small perturbation of identity mapping? This is something you can say x. d phi of x is x plus v of x. So this is a vector field. So in fact, you just need to put the metric on vector field. And so this vector field, it should be a Hilbert space to be able to define the metric. So you can play with that. There is a lot of things. We use the kernel Hilbert space, so we have a lot of kernel. Okay. You can play a little bit with this kind of thing. But okay, I think it's still in the same framework. And so other interesting question are how to put prior knowledge, how to do semantic reduction, it means how to capture just the sense of what's going on. So I think that's the general thing I have presented is not enough to really tackle this kind of question. So it's not, I think it's not sufficient to really do that. So I think I was very inspired by remember the paper with Anoush, where they try to have a more, describing pattern theory-oriented description of what's going on with the transformation. The thing is that the problem is that how you can make it very efficiently computational, how you can make things stable. I think this is really a problem. I think we can imagine a lot of things, but at the end we have to be able to compute things and so on. So I think it's really hard question how to do that. And so what I was told is I think it's also inside I think the framework, which is just to put constraint on diffeomorphism, to put constraint depending on the shape. And so it's mainly a work we've done with Barbara Gris, my former student, and Stanley Massachusetts also. So the idea is the first idea is to say, okay, if we try to think about to have some kind of vocabulary to describe deformation, what it could be. So you could say that you see the idea of modules, so it's a very simple idea. We could say the basic idea is to say we can have some kind of local transformation, local translation. It describes us. So it's something like that. Okay, no, it works. That works. Okay, so you could say locally you push something. You have something which is moving. You want to describe it. You can have what is this? Here this says the previous one. This is just the local translation, but it's a fixed direction. So you're just moving in this. Here, this is just to say we can think about describing that you can have a translation in many directions. You could have something like local scaling, that principle. So here we have something like we have a center and we have three directions. It's just spreading around. It could be something. We have this kind of here. You have this kind of location. Can you combine this to do something in shapes? Let's see. Or we can have a connection of It could be okay. It could be a mixture of. We could have collection of 3 centers and 3 translations. Okay, so here is Barbara Gris, with which we were doing that job, work. Okay, so if we try to think a little bit more abstractly of what we are doing, so we could say that the model is just defined by a different thing. First is some kind of, we call it a geometrical descriptor. It's just something, you could say in this example, you say it's something which describing is just a center and 3 points in, for instance, 3 vectors. You have something to describe it, just a description of your, and this could be something, a manifold. This could be a manifold which is now we have this, given this, we have some control variable. So it means that you can act, we can act locally, we can do something. So you have an H space, which is the control space, and you have to think about something which is very low dimensional. And given this geometric this descriptor of the model, and given the parameter, you can generate a vector field. So this is what you see, we have vector fields. So for instance, we've seen example for local scaling and rotation, and for local scaling and rotation, you have that, you could say for local scaling, you have just the center and maybe a parameter which is the scale, and you have to give the control is just a real variable, or you say this is the intensity of the scale. Okay, so we can have a lot of. Okay, so now the thing is that if we think about this model is lying on some object, so we have to describe how how this model will move when during the evolution, because okay, you have to think that we will have evolution of a shape, so you have the different model and they will move during the evolution. So how you move it? So you have to describe if you need to have psi, which is the mapping, saying that if you have a vector field, it's if you will transport your descriptor, how you will transport that. So how you transport the local rotation, how you transport the translation, it's more or less trivial. Okay, just to make it, for instance, you could do something like that. If you have local rotation, this is a local scaling, you could say, okay, if the background is moving, okay, you will transport the location. So you need to define how you do that. But you can do if you have vector, you have different ways. So this way you could say that if you have direction and this direction is just the normal to a line, you could say that when you will generate the transformation, this will move in the same way. So in fact, it's not always trivial to understand. Okay, so we need to say what is the model. We need to say how a vector field is acting on the geometrical descriptor, and we have to say what is the cost, how you pay to use this model. So because we will want to go in some kind of Riemannian setting, so you have to you have to define a cost function given an object descriptor, position of the module given the controls, how you pay for it. And we want to be something which is quadratic. So it's some kind of energy. So you say you will use different way to act on the shape, and you will pay for them.
The first part. So each one of them are vector fields, which is like a small diffeo. So
no, this is just a vector field. At the moment, you're just defining a vector field. Okay, just to make it more concrete, I was showing the flow, but you are just defining a vector field. It means, okay, I'm somewhere, I have different control, and I act on my control to try to...
But you said something about, like, you have one module, and then you have second module, somehow...
Yes, you will add, you will add, I will explain, you will add, yes, you will add both interaction, yeah.
Because it's non-commutative.
Of course, yeah. No, the addition is commutative.
No.
No, but after the composition, yeah.
Right.
You're right, but you will not compose it, you will do it simultaneously. Make sense?
Yeah,
okay. So what we have, we have this very mathematical way to describe things. So we have this M is a set of descriptor. You could say the center of the local translation. of the local location, whatever. You have your parameter. So now you have a product because at the given position, at the given parameter, you need these two things to define the module. You have the field generator. We'll talk a lot about that field generator, how you generate, given this parameter, how you generate the vector field here. You have this cost. This is not RD, this is R. And after you have the infinitesimal action, which explains when you have a vector field acting on the space, how this vector field is transforming the module. So you need xi, which is its mapping, which is say how the world is acting on my description. Okay, and if you have this, you could say, okay, you can start to work. So basically, usually people are not really paying attention on this part because okay, you have really to think about how this description will move during the transformation. Okay, so let's say for the choice of the cost, you could say this could be some kind of energy, but you could think about the fact that if you put arbitrary cost, you will get something which is just a mass, and maybe you will create a machinery which is completely unstable. So you could not say I put cost likely as I want. You could say I should have some kind of physical way to put cost, but it's not really easy to do this kind of thing. So in fact, the thing is that we could say, I think that the first thing we can think about when we work with this kind of deformation, we could say, in fact, we will generate whatever the control values are. We will generate the vector field, and so we could take a cost which is this cost of some kind of embedding vector space. So we can take this first something like that. But this is too restrictive. So what we can say is that we want the cost. Okay, this is maybe I should not take too much time on that, but this cost should be enough to control something like that. It means, in fact, to be able to show that you can define the dynamic and you have no exposure, it is a solution. In fact, you should say that your cost is sufficient to control this thing. But you don't need to have exactly the equality. The inequality is sufficient. So we call it this uniform embedding condition. We have said this is just a condition. Okay, so the thing is that we can have this silent module, which is silent module means that, in fact, on the shape, you could say you have, what is the shape? You can have this, you can have modules, and you can have something. But you could have also, for instance, a boundary, and maybe when you want to do match shape, you will need to have this boundary point of this curve. Because this is what you see, there is things you don't see. In fact, I would say there are a lot of things about the mechanism you don't really see, so you will see just that curve. And so these points, for instance, are not doing anything, they are just boundary of the curve, and so there is no cost associated to it, and no generation of any vector field. So you have it's trivial, some kind of trivial model. So you pay nothing and you generate nothing. But this is part of the global shape. So the global shape will be just the collection of all these things. Okay. So the idea is to try to do composition, to say we can have modules and we can concatenate them in bigger ones and so on. So we could, this is, I think, sometimes this is still true. This is, okay, but the question is that can we have this kind of composition? So we have some very simple and preliminary answer. We say, yes, there is something we can do. It's additive combination. So if you have different modules, so what is the combination? It means that you will collect all the different modules and you will make it from them. You make a bigger one. Where what are you doing? In fact, you will. This is an English question. You will add all the different vector fields. So the resulting vector field at the given time will be the sum of all the vector fields, and you will sum the cost. You will add the cost. I think it's quite natural idea. The good thing is that you have the stability of the combination under this additive combination. I mean, if you have cost which satisfies this UDC condition. If you do this combination, you will satisfy also. So it means, what does it mean? It means that in fact there is some hope, okay, in that setting to be able to compose things. So we have simple things and we add them together and we have something which has the same properties, so we can, if we know how to do it, we can say we have a bigger module and so, okay, this operation makes sense.
But there was some issue. If you can, I remember this was not an easy. If you concatenate small diffeos, because
We are
it's an
not
order.
concatenating. We are adding, for instance, we are adding the cost. We're adding the vector
You are adding the vector field, which is not same as concatenating the
No, it's not the
diffeos, right? So, but then what's the mean? If you have a large deformation from a linear.
Okay, so
you
maybe
cannot
to
break
make
it
things
up.
more concrete, you could say that if you have something like that, and you have something which happens at the global scale, you have the shape which is moving globally. So you have this, all that stuff which is. And now if you see on that shape, you could have something which happened at a small scale. So
They should be far
you
away
could say,
from each other.
okay, you could have a module which is looking for something which is local and something which is global.
Yeah.
And okay, from your point, you will need to add both things just to explain everything. So you have this global movement of the shape and this local thing. So you need to add. But this small module can try to explain locally what's going on. So you add things. And it makes sense because you are filtering, you have different layers. So it makes sense. Okay, I should. So the thing is that we don't need really to go into this. Okay, it's quite interesting, but okay. The question is that can we build some kind of Riemannian structure on that? Can we define something where we can find distance? Okay, the right notion is subriemannian structure. It means that because at a given position of you cannot go in all directions. There is some forbidden direction. So you have to pay infinite cost. Here, because why we cannot go everywhere? Because you have this parametric setting. So you constrain where you are, and this constraint depends on the position. But the thing is that we can show that given this condition, I think you could say, okay, we don't really care about that, but okay, numerically, if you have lots, it will say that you will have to try. Yeah. You can define some kind of optimal transformation. Okay, you can define this. So in fact, you can create a lot of it. Okay, so we can try to compute atlases. So I will skip this because I want to speak about. So just to show, okay. Okay, I know that I'm speaking in front of very serious people, so I'm sorry about showing this. I cannot say anything interesting, and I'm sure that it's just a ridiculous example. But okay, this kind of thing we are doing. So we have all these different scales. I think that you should recognize some of them. We are somewhere. And so the idea is that, okay, if you have these different things, so can we try to apply this kind of modules just to make in this kind of situation? So just to show, what we would like to do is to do something. We have different scales like this, and we would like to do, in fact, the kind of thing we can do is to try to optimize some kind of template. You can try to put some kind of modules, different kind of modules. It could be small rotation at different scale. It could be scaling, it could be translation. So there is the coding. I have no time to enter into this coding. So you have different description of different events here. And so what you would like, the kind of optimization you would like to do is to say, given this shape, this bunch of shape, can I try to put this modules, create a template, and to put these modules at the different places to optimize the position so that now I can explain the different shape. So in fact, this is what we can do. And so you have this kind of optimization where you get something where you have your template, which is somewhere, it's somewhere between all these guys. And now you simultaneously you get some transformation. So now you will be able to go from the template to any of the objects. And now you could try to read. Here this is the local scaling at a given scale, so it means that you have this, the scale is growing like that. And so you could see you have this red saying that in fact you have some kind of intensity, so you get some parameter of the, in the transformation, you get this means that you have this is, okay, so that's clear, when you see this picture, you see that the curve growing like that, right, this part. But you have some shift, you have a lot of different signs. I don't know if it makes sense to you, but okay, this is more or less some kind of idea to be able to describe the different, not just to compute distances, but to describe where are the differences and what's happening. Okay, so here you see the evolution. This is the geodesic, going from the first to the second. And so you could see the different parameters, what you need, all the ingredients you need to create to go from the one to the other. So it's some kind of description of the okay, so here you see and you see that, okay, at the end you see the grid, so you have this grid. Okay. So, the thing is that you could say that, okay, we're happy with that. It's quite hard to do. But what we have done until now is to use some explicit generative models. So it means we describe something, we say, okay, it's a local rotation. Okay, you can create some more tricky modules, but more or less the idea, you start on something you describe. So that's simple, that's explicit. But I think, okay, the global evolution will be a addition of all the contribution, local contribution. But the issue is that I think in this, if you look at all the modules I have given, there is no simple way to describe the relative evolution of length and proportion inside the shape. I'm describing somehow local scaling, okay, that's okay. Local translation is not saying so much. Okay, it's saying globally, but it's not saying what's happening at the position. So if you think about this, I think there is some flaw in some sense, is that, okay, we would like to be able to work with this kind of thing. So if we think about this, when you have this shape, and you go from this to this, so it should be maybe a neck. So what you want to say here is that, in fact, there's some kind of stretching, local stretching. So you want to have this, or you could say maybe you have some knowledge about that, and okay, this is local stretching. This is more or less what you say, what you see. You say there is stretching like this, or you say that you wonder if the stretching is uniform or if it's distributed along this. Okay, this is the kind of thing you would like to do. And none of the previous modules is allowed to do this kind of thing. So if we have to think, we have to say that it's, unless we were working with order 0, not exactly that, more complicated than that, but okay. Order 0, which is order 0, it means that if you look at the local behavior of a point, so you move, so you go from one position to another by just adding some kind of translation. But what we need is more order 1, it's some kind of local stretching, means that you compute the distance between 2 points and you want to see what's happening when you use the time. So, and this is, in fact, we need to have a local description which is related to compute this. What is the quantity which is important? But that is the infinitesimal straight tensor. This is the symmetric part of the differential of the V field at a given position, which gives this how the lengths are evolving. So we need to have this infinitesimal straight tensor. We can do it in 3D. This is I will do everything here. Why we have this? Because okay, this is a simple computation. Okay, C1 alone elasticity, but if you try to compute the ratio, between 2 point x and x prime at a given t plus dt, and you compare it to given t, and you do this ratio, you see that okay, you need to know at the first order, you need to know this straight tensor, and you get this where u is just a unit vector, given you have x and x prime, and I want to have the evolution of this, so u is that vector. in fact, what we would like to say is that if we think, okay, planar shape, we have to say that, in fact, we have this object, we have some line like this, and we have some local vector, we have some, maybe some local orientation R, which is a frame, which is attached to the object. And, or you could say this is a way to go from your object space to the ambient space, to the world space. Okay, so in fact, what we like to say that maybe we know something about what's happening. We know that there is some layers, or we know that there is direction like this. And more or less what we want to think about the modules, to say something about that. So maybe it's a very intricate, and we have seen so many intricate mechanisms creating things, but we could say as a description, how just understanding what's going on. What you want to say is to say something about what's happening. And I think that when I've seen that in many situations, you can have some kind of ideas about what's going on. So you want to introduce this. So, for instance, you are maybe more interested in this coefficient, how it evolves, what was the behavior, and maybe on the distribution of this R. So I think what we really want, okay, I think that interesting is to describe the pattern of this coefficient during the evolution. What's happening? But I think we can, usually when you look at shape, we can have a fairly low dimension description of this. We know more or less that this is globally stretching like this, or maybe we don't really know. We have data and we want to test this, so this is uniform, this is not uniform. We have maybe some landmark, we have maybe some contour lines, but we have to put some prior, because usually we have a lot of missing information. So that we would like to say, okay, I know this kind of behavior. So you could say that more or less the pattern, not the orientation, but the way, if you have a leaf like this, I don't know. In front of biologists, I'm very afraid to say very stupid things. You could say, okay, it's growing like this, and the expansion is small like this, and it's more and more fast, or this is the opposite, or you want to say it's going in the direction here. You have hypotheses like that. So you could have some. You could say, in fact, you have a structure. You could define quite easily. You could say, okay, I have a line like this, and more or less this should be more or less a uniform. And so it's easy to say this kind of thing. And after that, you can have some freedom. You could make it straight like this. So it's mainly the main axis. You have polarities, and you want to describe this. So this is quite easy to do. So the thing is that, in fact, we need to build something which is implicit, an implicit module, where we define, we say that what you could say at a given position, what will be my control. I will say, I have what I know that if given this vector, I will say that I want to say something about the stress, the strain tensor, So I say that I should have the kind of thing I could have. I don't know what will happen, but I could have some kind of evolution where I have constraint on this strain tensor. So I have this rotation is given, this orientation are given. Now I have that structure. We say, how this, what are the parameters on this? I have this parameter, and I put a constraint on S. S is the, epsilon I, the vector field, you put constraint on the vector field at this location, is the strain tensor to be equal to this thing. So it means you say, okay, maybe it will more clear, I will show you. So you could say, that's a way to say implicitly, you say, I want to have something which is growing the direction. You say that. And so you say, now, what will be the resulting vector? And so you could build something quite easily. You could use your one of your favorite metric and to say, I will minimize this quantity. So given my control, now my control is describing something which is related. Given my control, I minimize this, and I get a vector field. So now the connection between my control and the vector field is the solution of some kind of linear problem. So you have this. It's implicit. But I think it's implicit, but it's much more simple if you want to try to describe something. Right? Okay, so you see that here you have to constrict. No, you have to solve. This is something for a computer. A computer should be able to do this kind of thing, not you. So this is for a computer. You have, and so now you have this implicit mapping between your control and the vector field. And the cost can be what? Can be the cost of your vector field, the resulting vector field for this metric, or it could be something different. Okay, it's not clear. Okay. So I just want to use something, okay, a very simple example. So here what we have. So the blue points are related to this constraint of order 1, about the string tensor. So you have these blue points, I guess. And so here what I am saying here that more or less I should have the same string tensor everywhere. It means that the coefficient should be the same here and here. This is what I'm saying. Okay, no, I'm not saying that. I'm saying that I have a okay, so yeah. The thing is that, okay, we need to, okay, maybe I will click on it. So now, when you use your control, what's happening is that when you move your control, what you're seeing is that you are creating now, this module is creating this kind of behavior. So you see that you have a contraction which is uniform here, it's uniformly contracting here, and not moving in that direction. So this is the first parameter, you can have this kind of thing. And you can have I have a problem with my trackpad. Here you have thing like this. So this is all the parameters. So you can see that more or less what you are expressing, what you are saying is that when it's stretching uniformly. You can do it another way. You could decide, you could say, in fact, or you can want to test that it's not uniform. But you have your two parameters, you have some kind of core description on what should go in, and you want to use that. So you can put some anisotropy. You could say, in fact, the stretching is augmenting from the left to right. So it's easier to stretch in the direction. Okay. So if you do this, I say it's easier from the left to the right. So now I'm using the horizontal component. So what you see that in the stretching, it's not so easy to see, but in fact, okay. In fact, you can make it as visible as you want. Here you can see that the stretching, you have more stretching here than here. So kind of thing. And so now if you look at what's happening when you change the parameter vertically, what you will get sorry. Yes. Okay, obviously you will get a resulting vector field will create this kind of bending. Because you say, okay, you have this kind of the inhomogeneity from left to right. And so I was very happy. Okay, this is very I was very happy to see this kind of thing. Okay, and so if you now the angle, so you could say here I'm saying that you have the two principal directions like this, but now you can think about something where you put direction like this. And so what you will get, I think yes. Oh my god. But the thing is that, okay, here this is just two-dimensional, so you want to give this more or less a spirit of something which is unparameterized. Something which is, so you have to mix, how much I have?
No, I don't know. I was just back to the question, there is an ordering. I mean, you can't just add them up.
3 minutes. Okay. So the idea is that I really want, okay, not to just to put some parameter, I think. I really want to use something where I can really follow some shape and learn something and deform one shape to another. So I need to blend this with something which is non-parametric. And so the thing is that you can, a way to do it is to put ordered 0 points, which is kind of lengthwise. On the top of that is different modules, just the basic modules we have seen. You add on them on the shape. So this is the red points, you have the blue points. So the blue points is what? It's a point where you have a location and you have what is the geometric description of this? This is the position and this is the rotation matrix. For the other one and for the other viewer, this is just points. And now you add the two things and you have this cost. You add the two costs. So the first cost is the usual cost, I think the usual LDDM cost. And this one is the new cost we have on this one. And you could have coefficients. And now, playing with these two coefficients, we're mixing, we can go from LDDM to something much different. So we can move in this direction. Okay, so the thing is that we have to say what is the infinitesimal action. So how we act on this descriptor. So on point is just by velocity, and in fact on the rotation you will apply the anti-discrete symmetric part of the So you can solve, I will skip this, maybe it's better just to show to go to the questions. Okay. So here you can build a Riemannian setting, and so you can just look at what is the shooting, how you can shoot now from given position. So this is example. This is very, very recent work, I should say. This is not the work of last night. So here, what that is. This is the usual way. Here, I put a very small cost on the other one, a large cost on the other one. So it's just using the order 0 time. So what we see here, this is a typical LDDM behavior, where it's, okay, the movement you see that it's going in that direction, and so it's spreading around, because, okay, this is more or less the property of the metric, which is doing that. And you could say it's a bit annoying, because you see that's a very large thing here, small thing here, and it's looking like so lambda equals 10. The lambda 1 equals 10. So this is a coefficient. I pay a lot to use this modules, the blue modules. Here, this is more or less the same. I pay the same price. And you see it's and here I put, and so you see that this is completely homogeneous. Okay, you can put some anisotropy, so maybe this one is match. So if we put some anisotropy, we can have now this behavior. Okay, so maybe I will stop it. So the conclusion is that I think there is a way to try to go into this, to put some kind of interesting prior information, and maybe to work with it. I think we spent with Barbara some time just to think about the fact that computationally, is this possible to do it? So in fact, okay, we can see that there is a, computationally that's okay. I think what you have is that you should say that you have inversion, but in fact you have to invert the number of systems which is related to the dimension of the control. And so it's low dimension. So it can be done, but okay, there is a lot of, I think, things to study. We have not done yet a full shooting to say how to move from one shape to another. I think it's not so hard. To GPU implementation. Okay. Thank you.
Questions? You already asked your question.
All right, you go ahead.
I don't have a question.
Oh,
I just wanted to censor you.
I mean, there is an identifiability problem here from template to target. I mean, I still don't understand how you can just add the elements of Lie algebra. When you apply these
adding vectors, that's.
I know you're adding, but they're not in biology or in growth. They're not acting simultaneously.
There is a lot of weird thing in subriemannian geometry. Yes, we know how to go, because this is really about when you go from A to B, you cannot go like this. Maybe you have to take some.
There is an ordering to these things, and the moment
No.
there is
not
a time
here.
ordering.
Not here yet. There is no ordering. It's not the same if you say you are composing
Diffuse.
this plus this, but
Yeah.
now if you reduce it and you are doing, and you go to the limit, this is what you are doing. So it's continuous. Now there is no problem.
I mean, somehow you're doing more complicated thing and you have less problems. This is interesting.
Sometimes life is like that.
And also there was this identifiability problem. If you have a large deformation, how, do you have a unique representation in this finite
My hope, what I like in this, and maybe in the audience, maybe this will ring some bell, it's really to say, okay, to put this object in the data and to get the parameter out from it.
Yeah.
Say now, okay, can I read the parameter and say something interesting?
But is it
Just to
unique?
use it actively to test something on the shape.
Is this unique? This representation? Is
No,
identifiable?
no, okay, no.
That's not identifiability.
It's not cheating. So there's a lot of problems, but I say, okay, I think my impression is that it can be used to say, okay, when you have this reasonable shape and you want to test something, because I could show you, you can create geodesics which are absolutely geodesics which are very different from the kind of identity you have. So you can bias, and I think it's okay. Maybe I hope will be usable. This is work in progress. Any more questions?
In the case of large deformation, do you
Yeah.
think it requires some sort of rematching so that the error-
Somewhat?
rematching so that because initially the mesh are uniformly distributed, but in large deformation
There is no mesh. I'm not using any mesh.
But the let
Yeah, you are. You are, because these coins are representative of a mesh.
Yeah, in a
Yeah.
sense, but this is important. But in fact, there is no mesh. There is something I think you could build this example by just, you have your shape and you say, you click on this and you say, okay, I have to put things. So you could say that's a good mesh and you put this. And you say something, I have, I don't know, things like that. Orientation, and that's it. In fact. Okay, but that's clear that if you expand a lot, okay, maybe you have not enough information. So there is scared. I'm not tell everything about that, so I'm happy to have
Your
You
module,
have
I mean, if you start with a very small thing before
Yeah,
expanding, then your module will have to divide somehow. You will need more modules.
Yeah, but I think it could be, I think it's like growth. You have more cells.
It's not a fable.
So it strikes me that what you're doing here is really in the language of groupoids. So I don't
Yeah.
know if you know this language. But it's really a sort of local symmetry language where things are very much localized and so on. So I'm not. This is not. I mean, I don't have anything serious to say about this, but it just seems like that it's working in that language where you deal with local symmetry, local diffeomorphism, and so on, and then you have the question of when you can compose them, and that's
In fact,
that's
yes,
the right-
exactly. We are composing that. I think it's about flowing them.
Yeah, well, that's what it is.
But the thing is that okay, we can really enter into the math, but it should be another talk. Okay, thank you very much. So before we conclude,